So here we are supposed to speculate. So anyway, I do it. All my lectures are speculative, so this will be kind of double speculation. So you must be ready for that. Don't complain, yeah? And so I want to emphasize, of course I cannot talk about this all the time, the questioning in mathematics. And so the point, yes, you know, there is this citation, the dictum of Socrates saying that you know nothing, which is certainly impossible to understand what the meaning is, but the possible interpretation is that you must be focused in trying to realize what you don't understand, yeah? So you have to have a mechanism of asking questions, which is not so easy, because as we know from experiments in psychology, if you bring up kitten who only see horizontal lines, and they go outside, they don't see vertical lines. They're stuck into the vertical objects, yeah? And so we are exactly brought up this way, yeah? We only can see what we are supposed to see. And what we're not supposed to see, we're just blind to that, yeah? And so the question how to break it. And just, so I'll give some instances in the history when people saw something, and sometimes it was efficient, and so we're asking good questions, and well, some questions happen to be not so good, apparently. And so I look at some particular subject, and so I'll be speaking about geometry, so I'll concentrate on the most visual part of the geometry. Of course, geometry has many aspects, and you can ask questions on different levels. So just visually, what you can realistically observe when you can ask questions. And again, the problem is that our visual system works in such a way you only can see what you're supposed to see, even that's in the real world, yeah? So if some person moves in a slightly different way, it becomes invisible. You notice, yeah? So it's only very canonical patterns which we can see. And even those we apparently see, well, we don't see. So I will be speaking mostly about geometry of metric spaces, so when you have a distance. And I don't know, of course, the history. I don't pretend to say something about history, so my historical statements will be just, shouldn't be taken seriously historical, yeah, it's just mathematical folklore. And the first, at least in my knowledge, where the metric appears, the object not only attached to the Euclidean space. Of course, when it comes to the Euclidean space, the metric was discussed already, Zenon paradoxes, whatever. Extensively, they were trying to understand if topology of the space forces the metric. Yeah, this is one of the discussions with Zenon like that. But the metric for non-Euclidean situation, I think, appeared first in the Gauss work on surfaces, yeah? So, is it true? Maybe somebody may know better. So you look at the surface and the free space, and you start thinking what you deform the surface as a piece of paper, right? And then something doesn't change, and the something is the distance, but not as measured in the ambient space by straight line, but by the minimal shortest curve inside of the surface. So this was for all I know, again, was the first instance when people, Gauss kind of brought out this new conception. I don't know how he articulated that you might have a space, and kind of a rather simple-minded geometric space, when there is a distance function attached to this, which satisfies the triangle inequality. Right? So you have function two variables, right? And you know this ABC property that C is bigger than A. So yeah, A plus B. And by the way, here, and I come to that, you immediately may ask a question, because, so this is a function two variables, which must satisfy this condition. What is R?
Real valued function.
Yeah. And so what? Satisfying the triangle inequality. And of course, the immediate question which appears, and this is just often we meet this question, how we can find such a function. Yeah, it's quite difficult, actually. You have function two variables, you must satisfy this condition. If you just think about for this function two variables, write it down by formula, right? You'll be in trouble. Then to proving it obviously satisfies this condition. And this will be one of the, it's not just checking something as positive or not, yeah? It must be true for all pairs of points, yeah? It's not, and again, I shall come to that, yeah? This is one of the general issues about generating objects which will have it, yeah? They come in this example, but in general not. And so there is this deformation, and then that And so I guess the question which Gauss could have asked. So now I have one surface here and another surface there. And of course, in this Euclidean space, you can see easily either they're different. You in the plane, you have this arc and this arc. But internally, they have the same length as arc, so they're the same. How you can tell the two metrics are different? They're not can be matched one to another, and so with respect to this internal distance, they will be indistinguishable, right? If we live inside of the surface, we wouldn't know the difference. And then he introduced curvature. And in a certainly extremely ingenious way, which this cannot come out of simple questioning. This was a kind of mathematical point. So you look at the unit sphere and you take this normal vectors to one surface and normal vectors to another surface, unit normal vectors. And so it maps here, and this also maps over there. And this map, so has a Jacobian by how much it distorts area, yeah? So we take tiny little element of area here and have tiny little element of here, and there is some ratio between here, and you do the same there. There is another ratio there, so the Jacobian of the map. And so he observed that the Jacobian of this Gauss map does not change when you deform the surface, yeah? So it's intrinsic characteristic. So it's defined, again, in the Euclidean terms, but a posteriori, it happens to be invariant. Yeah, that's certainly extremely simple way to prove, but extremely, I think, impossible to guess if you don't know that. Yeah? I just wonder if ever such questions were asked people who don't know that, like students, if they can tell the two surfaces are different and if they can reinvent the Gauss map. Yes. Because you see, it's very difficult to evaluate very impossible to evaluate kind of the difficulty of making such a conjecture. For me, it looks impossible. You must be a genius to make such a guess. Yeah? But indeed, it's not so. Well, this actually we don't have a mechanism of evaluating this kind of statements. But okay, so and in particular, so in this I'm coming closer to what I want to talk about. More comes the crucial distinction between positive and negative curvature. So another kind of object which I believe, actually I don't know who first isolated this. This is convexity. Yeah? It's one of the big ideas in mathematics and starts from something very simple. You know this is convex, yeah, and this is not convex. And before you know any mathematics, of course, you know that somebody is convex and somebody is not convex. Right, yeah? Coming up with a definition is, again, it's not that difficult. I think just, well, almost everybody with mathematical elementary training, I mean, just at a very limited level, can work out a definition of convexity. However, again, it's not so easy. Once you isolate it, convex it, and you see gotten convex objects, so I have convex ones. How you start asking questions about them. So as a mathematician, what you want to know about them. Yeah? And again, it's not that easy. You have to ask a meaningful question. Well, they're convex, that's all. Yeah? So, but you know, it's not so. I mean, there are quite profound questions. One, just in a second, I say about dimension, two about surfaces. But, and I don't know if somebody will talk about that as we understand now. With Tali, kind of, you know, we may take more that the convexity is power emerges only when dimension goes to infinity. Yeah? When dimension goes to infinity, then convexity really tells you more and more and more. And any fixed dimension, convexity tells preciously little. Yeah? In a fixed dimension. I'm not aware of any really profound convex theorem which is already kind of significant in small dimension. Of course, there are some results where involve convexity, but they're kind of tangential. Again, you know, I'm supposed to be provocative. If somebody knows great theorem about convexity in three-dimensional sets, and so I must. But it's a universal statement in all dimensions, yeah. But but a real variety of shapes, yeah, in convexity appears only when dimension is large. Well, essentially because in every fixed dimension, the space of convex sets up to proper normalization is compact, and certainly they're all kind of before you. In a way, you think you know them. It's a question of computations. Though, as you know, computation may be formidable. Like, well, coming to question, there was this question of Kepler about optimal parking of spheres in the 3 space, and it was recently solved. And yeah, you know, the best arrangement of spheres in 3 space is just periodic arrangement, and which is specific for the 3 space. And what do you think is a good or bad question, by the way? Asking how many. Because somebody proved it, yeah, so I cannot say it's just junky question. Hmm?
Probably more important scientifically than mathematics.
Do you think, again, we can say, well, because in physics things are being arranged this way, this is what you mean. But is it really physicists would sign under that, yeah? Do you care? Jürgen, do you care that the best packing in the 3 space is by round spheres? Where's Jürgen?
I wouldn't care
Yeah. Yeah. Because still, yeah, in physics you cannot prove it, yeah, for realistic systems, yeah, and when not crystallizing somebody, so you cannot use the theorem, right? So is it of relevance for physics? I don't think it's, I cannot just tell for physicists, yeah, or for biologists who crystallize proteins whether they care for that. Of course, yeah, this is in mathematics all the time. We're just between two dangers of triviality and irrelevancy. Yeah, when you prove a very deep theorem, it will be very easy to be irrelevant because it goes somewhere there, or it may be very relevant, like this theorem of Gauss. But I can imagine a modern mathematician being shy to publish it because it's so trivial. Yeah? So. And certainly this thing about spheres is extremely kind of difficult theorem, but you know, it looks to me irrelevant, yeah? I mean, I don't know. Again, I won't just opposite opinion say it's really relevant. Yeah? No, about taste, yeah, again, when we say the matter of taste, we immediately kind of make further discussion impossible. I don't think there is such a thing as taste, yeah? Right? So, actually, at the end, I will say what kind of criteria, what determines, yeah, our orientation in the matter of taste. I mean. Hmm? Yeah? No, of course, yeah. No, I'm not saying about to happen in the future. Maybe 10 years from now, there will be something grand coming from that. I'm saying at the present moment. We cannot judge by they use the standard of the future. But the present standard, yes, if you think about the theorem and what goes into that, yeah, it's just essentially computational, right? Or let's take more elementary question: how many balls you can surround given ball? Yeah, there was a discussion between Newton and somebody. I forgot whether 12 or 13. Yeah, it's purely computational question. You know, even at that. Which one? No, but again, it's not computation, but it's reducible to computational result. And it's clear that there is a hierarchy of computational things, which one of them will imply. Yeah, so it's quasi-computation. So this is a systematic computer search which give you yes or no. It may go forever, but it's not. Yeah.
What's your view of the full color theory?
No, I'm not supposed I'm just asking questions, yeah? So I'm asking questions, you're answering them, yeah? So what is your view of the four-color theorem?
I think it's very similar.
No, four-color theorem is less computational, no? The reduction to computation there is non-trivial, but for this case, it's always a computational scheme which reduces. Yeah, they're different in structure. Okay. So, where was I? Huh? Okay, so we were about the convexity, yeah? Now, so comes the distinction of curvature. Yeah, so we have convex surfaces, and we want to again to make kind of a big thing out of them, just to extract something and generalize. Yeah, that's one of the way we make questions. And so, as Gauss discovered, there is convexity and there is this opposite case, not concavity but being settled kind of surface. They always have difficulty of sketching. Yeah, and such that like when you map them to the sphere, this kind of, they don't change orientation of the map, so here is the surface, and here is the sphere, and these vectors kind of don't switch, but if you make this, for this surface, yeah, there is switch of orientation. This oriented thing goes to the opposite oriented thing, yeah. Well, it's not so easy to visualize, by the way, yeah. Orientation, you know, is a tremendous mess, what is plus and what is minus, but believe me, there is a well-attached sign to this map, and of course you see it in the space. Saddle surface is very different from convex. And so intrinsically, the convex surfaces characterized by something being positive, some curvature being positive. Or the opposite thing is something being negative. And they're so very visually different. And then, well, we want to make a, it would be nice, yeah, to paint them. So yeah, meanwhile, yeah, you may ask questions, yeah. You did it, yeah? And so in the framework of abstract metric spaces, so how we can isolate this convexity. So what convexity means in the framework of the abstract, or these opposite things of not being convex. Or say hyperbolic, yeah, that's opposite case, it's hyperbolicity. So there are two kinds of words, of course, as I can speak, different question. One, convexity, which we kind of have visual image, pretty good one. And then another opposite, hyperbolicity, which I think by far less clear in our mind, yeah? We see convexity, recognize it, again, our visual system much better, recognizing convexity rather than hyperbolicity. Easier to imagine convex than non-convex. So, and for convexity, how you define convexity for general spaces? Of course, I will not give you the historical definition how it was, but just give you one of the recent elegant characterization of convexity. But so the objects are, so they are metric spaces with a distance, and as a surface, at the moment, I want to insist that the arc spaces, so for every 2 points, there is a middle point. So the distance here equals exactly half of the distance between 2 points, yeah? So this is this kind of metric. So you can always find intermediate point, as the case for surfaces over whenever again, when 2 points, distance measured with the shortest path between them. So but this will be mostly space I'll be concerned with at this stage. Now, how we can define positive curvature in general? And there was actually a long process, yeah, and work by many people, especially by Alexandrov, who actually recently died. Maybe we heard of this, yeah, Alexandrov, who developed axiomatization of this conception. But kind of the easiest, the shortest, mathematically most conceptual definitions emerged rather recently, and it's impossible to guess. What it is as follows. So I have a symmetric space X, and convexity means the following, that if you take any Y instead of X, and you map it to any Euclidean space, well, from n maybe 1 up to infinity, so I have a map F, and suppose that this Lipschitz of F less than 1, which means the map is distance decreasing. Right, so it makes distances smaller. Then it's extendable to some map here, yeah, with the same property, also distance decreasing. It's logically very simple, yeah, but it still takes time to absorb. If you speak about just functions, then on any space, you can extend functions, Lipschitz function from smaller set to bigger set by kind of trivial reasoning. This property is true, and this is non-trivial, if this is Euclidean space, yeah? If you put here Euclidean space itself, and this is Kirch's, I cannot remember the Kirch's-Baum, oh. Kirch's-Baum, yeah, Kirch-Baum theorem or something. who proved this, yeah? That's already a theorem saying that if in Euclidean space you take any subset and consider that such map into another space, then the map extends. The map extends to the whole space. That's a non-trivial theorem. It's just, again, proving it, not that difficult. But asking such a question, not at all. And then this property, you can ask what are spaces in general having this property with respect to mapping to Rn, and the answer is exactly those which have positive curvature. For example, if you take a piece of a convex surface inside of the Euclidean space, and with this internal distance, it has this property. Which again, if you just start from scratch, that's not so easy to prove, yeah? You have to develop the geometry of the surfaces, starting from the fact that they're convex or that when they map to the sphere, the curvature is positive. But, so this looks extremely convincing. Yeah? This definition makes it being so nice and logical, and it's true for Euclidean space, true for surfaces, and does it give you a consistent class of objects. You start thinking about them, and they go graphically. And in the case when you have a Riemannian manifold, in a second I will again discuss Riemannian manifolds from this kind of a naive viewpoint. What's good about them? This property expressible in terms of the tensorial calculus, positivity of the curvature. And there was much work dedicated to that, but still, we have kind of a highly non-trivial theorem, but still there is a big question of the relevance of the whole theory. So, for mathematicians who know that, yeah, you know, a big developed subject of space of positive curvature, the question is if they're relevant, though they generalize convex objects in any dimension. You have a convex piece of a convex hypersurface. Intrinsic geometry had this property, so we have a class of examples. So they kind of generalize convex sets, and in many respects we know they look like convex sets. There are quite a few theorems. However, the problem is, and this is often happens with mathematical objects, we have very limited ways to generate them. How to generate such objects? I'm not speaking about constructing examples. With certain efforts, you can construct examples here and construct those there, but generate them at least in a way that if you, on one hand, you have the generating mechanism, you generate the surfaces. On the other hand, you have theorems about those spaces. And so, if the situation is such that if you take this theorem and apply it to this object, it still remains a theorem. Right? Because what happens when you take any theorem and apply it to any object in nature to generate, you know this anyway, yeah, in the generating mechanism. And this happens kind of very, very often in what we do. And you know, this actually generation of mathematical objects, I'll come to this later again, it appears everywhere. For example, recently I was in a similar kind of similar meeting in Rome, and I spoke to Mumford, who is now certainly out of algebraic geometry. And I made a bet. He cannot show me more than 10 ways of generating algebraic varieties. He says, oh, immediately I give you a dozen. But he stopped about 5 or 6, yeah? So we say, give an algebraic variety. So just give it to me, I mean. One from you, and then immediately you stop, yeah? You cannot generate them. Say, convex sets are good in this respect, yeah? You generate them, you just take hyperplanes in the space here, and there, and you have it, right? And they're easy to generate. It seems at least easy, yeah? And then you have to read off from this generation. But for this particular instance, unlike convex sets, so you have convex sets with a tremendous pool of examples, but then it essentially stops. So there are some series of examples about which you know everything, essentially coming from Lie groups, and that's it. You just, not just examples, again, you can, with efforts you can make something and produce them. But you cannot generate them. They don't come by themselves, you just don't know what's there. And that's a big question. So you have a beautiful, intrinsically very rich theory, but what's in there? So actually this kind of grammar describing properties versus generation, yeah, was kind of very dramatically in linguistics. Maybe you heard, yeah. So before the work of Harris of Chomsky, linguistics was concerned with grammars as rules. So there are such rules and such rules and such rules. So the question there, mathematically quite simple. You have natural languages. They're a string of letters. So what mathematically you can say about them? What makes a language, yeah? And so what are rules? So there are grammars or whatever, semantics. So you limit possibilities. And I think, well, again, this I'm saying without really knowing the history. And I believe that before Harris and Chomsky, people were concentrated on isolating rules and describing rule after rule after rule. And amazingly, however, that still the rules were very restrictive. The rule of grammar are very restrictive. However, we do know there are lots of sentences we can generate. And then the next question is, what is the generating mechanism? And this is what Chomsky introduced, yeah? So how to create languages out of certain, coming from certain rules. Of course, this is kind of mathematical scheme, and certainly the more kind of trivial, otherwise it's more profound, whatever, but certainly it's a next level question, how actually a piece of meat can generate the structure. Yeah? So our brain is a piece of meat with no structure at all. Yeah? It's certainly extremely primitive, yeah? Evolved by kind of random stupid choice. And then it generates these extremely organized sentences. Yeah? How could it be? Right? And so this, but the generation is there. So there are, in the interesting structures we meet, we have both. We have very severe limitations what we can make. Yeah? And despite these severe limitations, we have generating mechanism which for some reason ends in this very small space prescribed with limitations. And so kind of mathematics, when it becomes interesting, exactly has the same feature. Yeah? You have grammar which restricts your possibilities, and then there are generating mechanisms. And so mathematics are more or less on the side of that you limit the rules you're allowed to, what kind of object you may have. For example, we suppose that the theorems which you state and prove must be correct, yeah? Which is a common assumption, but it's not all clear why we should stick to that. Yeah? No incorrect statements may be, in some sense, much more useful and more relevant, but they must be relevant, yeah, and certainly non-trivially non-correct. Yeah? If they come from interesting generation mechanisms. So we cannot generate them. Now, just, when I say about generation, and the same question I was raising before about metric spaces, how we generate metric spaces. So let's return back to that, yeah, before I enter into negative curvature. So how to generate metric spaces? And then there was this, the Riemann conception of a metric. And certainly it has many kind of other features, but just I want to emphasize one, a very simple one, about just generating metrics. And so from what you start with a quadratic form in three variables, so in the plane, yeah? And so you have three coefficients A, B, C. Describing a quadratic form, yeah? So secretly it's x squared, y, xy, and y squared. And you make them dependent on the point of the plane. So all three of them are function in three variables. So you have a family of these quadratic forms at every point in the plane. You have a quadratic form. I want to think about a kind of little ellipse, because we say they're positive definite. And that's very easy to write down, right? I can write down some function like, so symbolically you use this notation. This replaces x squared, and then, so it's a combination of these three, this Leibniz notation, I must say, I cannot take them, yeah? I feel very uncomfortable writing them. This notation of Leibniz, and here put coefficients, so it will be A, B, and C. And these A, B, C are functions. Just so what you have, in fact, three functions on the plane. They're easy to generate, and the only condition is being positive definite, which is easy, unlike being metric. So, and this you can write down just at will. And then from that you have a metric. So how you do that? Because at every point you have this little ellipse, yeah? You declare this vector to be unit. So given any curve, you know what is the unit size. You can divide it into unit pieces and count how many pieces you have, and this is the length of the curve. And then you say, well, given that, you take the shortest curve between 2 points. And the length of the shortest curve, my metric. By the way, that's easy to say, yeah? What's hard to make, to find the shortest curve, by the way, yeah? So this immediately generates a lot of metrics. But the price you pay is very, very implicit. When you say the minimal curve between 2 points, because if I write down the metric by random taking this function, I don't know, like e to the x squared plus sine x, show me this minimal curve, yeah? We can prove it exists, but evaluating it is a big mess, and it's a big problem. However, you do generate lots and lots and lots of metrics on the plane, or in the Euclidean space. Of course, you can pass to manifold then and say, well, now take a smooth manifold, right? And you make the definition. And especially say maybe be pleased when manifold is compact. But then, by the way, there is another issue. Just actually how to generate manifolds, compact manifolds. And if you just look at what happens, you see that we have very, very few general means of doing that. Yeah? And essentially, the basic mechanism, which is sufficiently universal to generate a manifold, is by taking it in slightly generalized sense as levels of smooth function. And you have to make the function generic, which is, again, a horrible thing to do because you just can't precise it very well, and taking the level. And that's about it. After given this manifold, you can do many things, yeah? I hate to say the primitive topology, like surgery, whatever, but this is peanuts compared to the first creation act. So this is kind of like a god, yeah? It creates a manifold. And then you can tinker with this, yeah, by something. But you can't create a manifold. So it's extremely difficult also. The mechanism of generating manifolds is not that easy. There are some, when I say manifold, I really want it to be just in my hands. And the second, they say what it means very much, not up to diffeomorphism or whatever, but really just physically manifold in my hand, your manifold. Yeah? And this is the most powerful general mechanism. Yeah? If you give me a manifold, I write this function and say, well, I'll take it on random, and then I have a manifold. But there is nothing else, I believe, in mathematics comparable to that of creating manifolds. Everything is much, much less powerful. I don't know if, again, I want you to say I'm saying nonsense, yeah? You just, okay, so what is the objection? Of course there are modular spaces, yeah, this is another source of space, yeah, I agree. Modular spaces, yes, what the second Manfred said that I have perceived there are modular spaces, is what after that? Of course? Of course, I agree. Modular space is a very powerful, very mechanism. Of course, it does something. I'm not saying there aren't, yeah? I'm saying nothing of that genericity and power. Modular space is a good source of examples, absolutely. No question about it. More? I mean, no, but you can think, you can think of something, but it's not that, it seems to be, it's not so.
Modular spaces in many cases are abstract and very difficult to find out what they are.
Yes. No. The modular space is perfect way. I mean, yes, this is one of the most powerful ways to generate mathematical objects as modular spaces, which was, again, emphasized rather recently. But that's one of the points. But so there are these random mechanisms, there are modular spaces, what else? Huh? No, just inside of mathematics, how to generate closed manifolds. Internally, give me 20 ways, different ways to generate smooth manifold. No. They're not generic. Equations, they're non-generic. That's the whole point. In algebraic geometry, you can say everything given about algebraic equations, but nonsense. If they're generic, you see manifold. If not, it's just words. That's the whole point. And modular spaces don't come this way. They come as extremely kind of it's exactly generating mechanism which give you something that's very high order structure. Yeah? It's a perfect example. Yeah, modular space is a fantastically good example of how we generate objects, and with very, very restrictive properties. Yeah, and the thing is just appears everywhere. Say in languages also, they kind of modular space or something. Yeah, this is why they exist at all. Yeah, and the modular of, well, we don't know of what. Yeah, of brain states. But coming to smooth manifolds, so in the end, I'll bring up some question. Yeah. Yes. No, but again, say most of the processes, but there aren't this most, yeah? There are very few of the processes. This is what I want to say, yeah? And my question is, one of the questions, how to generate manifold, yeah? Mm-hmm. No, but show me a quotient space. There are examples, of course, but there is no systematic way to construct it. It is, by the way, another issue. How to construct equivalence relations. So, of course, that's money. Come on, this homogeneous example, they're just peanuts in the whole world. But when you take quotient space, you have equivalence relation in your category. For example, you can say, well, take a smooth manifold, multiply it by itself, take inside thirds of manifold, which will be equivalence relation. Just show me that. I actually I will go to convince you in this way that even compact spaces don't exist, yeah? Because they can be defined this way, but unbelievable they exist. Because you can make equivalence relation in the category, and this is typically extremely difficult. It takes you out of category, give you your kind of spaces like foliations. It doesn't give you manifold. Hmm? Yeah, they're like modular spaces. They're usually not manifold, yeah. They're usually not manifold. They're spaces, but typically they're not manifold. They do develop singularities, but the way they just force on you, yeah. I'm saying specifically here about manifolds, not general spaces. So, manifolds are, and maybe, I'm wrong, I thought about this for a while and just was surprised to see that there are so few generating mechanisms for manifolds. Okay. But anyway, we do have this loss and loss of Riemannian matrix we can generate by this process, and some time-enclosed manifold as well. But there is absolutely no way to generate them in this category, yeah? And so this is a big question. If there is some differential geometric framework, maybe not that, but somewhat different, which includes convex sets, but in the context of general metric spaces, or Riemannian manifolds, or whatever, if you can truly generalize convexity, yeah, in this naive way. Of course, there are completely different avenues, like pseudo-convexity in complex geometry, which is much better than convexity, but it's another issue. It takes you away from naive intuition. Okay, so, and then, of course, the issue which appears here. So again, even if you're in this limited category, what are the questions you may or may not ask? And so I want to emphasize I have a wrong kind of question, in my opinion, wrong kind of question which you ask and answer, though I myself was involved much in doing that, just relating topology of the space to its geometry, right? So given certain topological type, even admits a metric of positive curvature. Yeah, and this is in my opinion, very stupid question, though you can sometimes answer it, yeah, because you mix the structures in the wrong way. So maybe here make some little diversion, because recently I learned of some question which came actually from physics, and it indicates how basically we don't understand topology. Huh? Before I go to negative curvature, where situation is more satisfactory. So this question exactly related to this of generation manifolds. So let's try to generate manifolds by triangulating them. So we just consider manifolds which are triangulated into simplices. And when you triangulate manifold into simplices, say fixed dimension k of your manifold, you triangulate it into n simplices. So how many such triangulations are there? And just simple computation shows, regardless of k, the number of possible triangulations will be of order n factorial. Whether they're manifolds or not, or complex, you have about n factorial different simplicial complex with n simplices. But now, let's consider among them those, so this space X and triangulation, which are homeomorphic to a given space. So you restrict their topology. And then there is a conjecture that their number of such is bounded by some constant to the power n. So it becomes by far less. From n factorial, you drop to exponential. And, well, for all I understand, it's still unknown, though there are books by physicists who just prove it and use it or whatever. I don't think there are actually proofs. And so it tells you that we're just looking at the space given to you. So triangulating is one way of generating manifold. You triangulate something and say, well, this satisfies my axiom. But the question is what actually tells you. Just even in very coarse, the coarsest possible way, you don't know how much topology restricts. Here geometry is just triangulation, is kind of a geometry. And then you just say, well, forced topology. And they seem to be highly incompatible. They just, to match a given topology by geometry, it's an impossible question. And I think it's, I learned about this other recently. I think it's a fantastic question, yeah. I don't know simply equation in topology, as you can imagine, and it was never asked by topologists. And if you just think about that, you realize that it's how little you understand about this matters. For physicists, I don't quite understand, of course, the relevance of this, yeah? It is relevant, yeah? No, but still, it's just very coarse, yeah? I want to know there is some limit and there is next term. And, yeah, exactly. Yeah. Okay, so much for convexity in this question. So, and now another aspect. So I was speaking, the problem we have is the generalized convexity. What about this opposite thing, hyperbolicity? Yeah? And this, of course, emerged much later, understanding of this hyperbolic thing. Yeah, so Gauss was inventing hyperbolic geometry, and then was done by Lobachevsky, who invented it somewhat later. And do you know why he did it later? Because they have the same mathematics teacher. First he was teaching Gauss, then he went to Russia to Kazan and was teaching Lobachevsky. It was the same man, yeah? Yeah, I think it's not a joke. He was a mathematician. He's not known by his name, but he was apparently a fantastic fellow. I forgot his name, but I was in Kazan. They gave me the name. I never heard it, so I forgot it. I don't remember the name, but he's some German scientist, and apparently he was extremely brilliant man. And he probably was asking this question to his students, yeah? And apparently what stopped Gauss from publishing his work, and this I believe was kind of a, well, maybe he understood something you don't see, that what he couldn't do, yeah, he couldn't find model in the 3 space, yeah. So there's partial spaces, of course, the negative curvature in 3 space, but you cannot extend it, and he couldn't extend them, and for good reason it's kind of impossible. So you cannot find the surface of constant negative in 3 space, and he would never look for high-dimensional spaces, where it still is extremely hard to find it. But certainly it's very easy to find it in the Lorentz space. Yeah? In the Lorentz space, the unit sphere is just that, and certainly it was out of the imagination of that. So there is this hyperbolic geometry, there is the whole thing coming from this whole idea of hyperbolicity, both in geometry and dynamical systems. Well, I don't want and cannot discuss it much, but here situation is, yeah, by the way, I was speaking about this definition. One very attractive feature, and this will appear also in hyperbolicity, it's fact it's kind of easy to verify. It's kind of because it's local. So if property, if you remember what I say, that any Lipschitz distance decreasing map extends from bigger set to smaller set, is a local property. If you have a space where this condition is locally satisfied, then it's globally satisfied, which is not at all obvious. Given a space where we can cover it by tiny little sets, on each of them, this is being true, then it's true in the whole. Yeah? And this, of course, one thing geometers love so much. Yeah? You want to start from something local, and this very property then tells you the same thing globally. Not just something, but exactly the same thing. Yeah? And there are not so many concepts with this feature. Yeah? That locality just becomes global, but without changing in shape. And so hyperbolicity can be actually characterized in a similar way, in a seemingly similar way. Namely, there we're speaking about maps from X to the Euclidean space, and when we speak about negative curvature, on the contrary, we map Euclidean spaces into our space. And just the same, just for any distance decreasing map from a subset extend to the bigger space in the Euclidean space. So it's completely symmetric. And also, locals implies global, provided, and this is little kind of provision, this space is simply connected. And so it may look kind of disturbing, but on the contrary, it opens kind of the really interesting possibilities. So again, negative curvature means that any distance decreasing map from a subset of Rn extends to the whole Rn when you map into the space. And if it's true locally for domain in the space, it holds true for the whole space, provided this global space is simply connected. Yeah. So, and then you can say, and up to some extent, yeah, in the all the development of negative curvature, there is different definition. Well, you have space of negative curvature, yes, and then while determined essentially by its universal covering, and becomes really having this feature. So there is fundamental group, and so the study of that reduces to algebra. Yes, I remember this statement written, which is absolute nonsense, yeah, because there is no algebra of groups. I mean, this, again, if you look at the definition of a group, especially yes, the one given by presentation, yeah, there is very limited theory there. Yeah, just again, group like other mathematical object, you give a definition, and then you ask what a generating mechanism. And then, of course, there are groups coming from particular structures. So here it's very different from manifold. Yeah, there are lots and lots of different structures. We just give you groups. Essentially, they're kind of modular spaces. They're automorphism of certain structures. And so, but they like Galois group. Yeah, but certainly it's not a group. Yeah, I mean, it's something very also a group, but much more. But internally in the group theory, the basic mechanism of generating groups is having generators and relations. So it's again, it's very simple to say and well, you have just symbolically you have your symbolic generators, and you have relations which are words in these generators. So just a bunch of words in a given alphabet. So you write words, say in English alphabet, and this gives you a group. Yeah, just take Shakespeare, it gives you a group. But the problem is, if this group is, what is this group? And typically it will be trivial. If you just do it, too many words, yeah, and things collapse. You know? So it must keep balance, and the best known mechanisms to control it come amazingly from negative curvature. So these groups which we understand, which we can generate, well, I don't have a chance to explain this, of course, but it actually comes from negative curvature. So it's one domain where this negative curvature enters and shapes it and explains it. And basically, one of the reasons exactly is this, that locals implies global. But there, local versus global of different nature. In positive curvature, yeah, the objects, roughly speaking, satisfy this equation. Yeah, this equals minus y. And so what you have this sign, and this is a rather unstable phenomenon. If you perturb a little bit the equation, you lose this simple oscillating behavior. Yeah, it may be like grow, etc. Yeah, completely out of control. That's kind of phenomenal dynamical system. They kind of elliptic periodic point. But hyperbolistic responds to exponential growth. You have exponent growing there, and this exponents are very robust. If you knew at every step you're doubling, you go double. Imagine you change a little bit, yeah, you don't double, but sometimes triple, sometimes 1.5, you still grow the same way, yeah. And that's the essence of hyperbolicity, or exponential growth. And actually, exponential functions another source of good questions. So, but it's not at all clear from these two definitions. One, they turn this way. So positive curvature limits you. And that's psychologically, well, people are divided into categories. You love to be restricted to something nice and pretty and cozy and kind of convexity, positive curvature, and in this little room, yeah? And it's very small, but well, you can study it in great detail. Or on the contrary, you have a hyperbolic. You go to infinity at exponential rate, and then you just still want to know what happens. And of course, in the dynamical system, yeah, it's the same kind of phenomenon. So hyperbolicity is persistent phenomenon. And both in geometry and the dynamical system, in most cases, you don't have pure hyperbolicity. It's just mixed with something else, like this convexity. However, it's dominant, yeah? And again, when we say that in general dynamical systems, actually it's not here. So you want somebody to object, yeah? You don't object, yeah? Okay, good. Yeah. And the only class of system we may hope to understand where there is, by shape is given by hyperbolicity, though it's not pure hyperbolicity. And the same is true about group theory, which I cannot explain. Okay, so this I was supposing to mean to be non-speculative part of my lecture. Yeah? Now, where we start kind of speculating. So I showed a kind of example of a simple question how it developed, and then we just want to just also ask questions. So Gauss asked this question, and that gave us good development. So we are not that smart, but still, how to ask questions? So you in a very simple domain, you just have your objects. You just take your simple mathematical mode. See, in geometry, I emphasize kind of extremely visual kind of situation, which we do know. We don't have to know mathematics to ask the question, but how to isolate it from kind of from possibilities. So, unfortunately, Arnold is not here because he had this conception of how it's called multi-mathematics or polymathematics. Yeah, it's some way you have something here, you move it there, and just how you generate questions out of anything. Of course, if you just do it by will, you don't expect really good questions. But even bad question I would appreciate. Yeah? Just how to make a bad question, but not obviously trivial. And where, so we look. Again, I don't really mean profound questions, yeah? Which kind of border with conjectures. Yeah? But I mean just very simple-minded questions. You see something and just, well, there's a certain pattern in that. And so some of them may come, of course, internally mathematically. So now I will say something I was thinking recently myself, some way of generating objects and therefore asking questions about them. So one thing is you just find some generating mechanism for objects, maybe not especially bright, but ask questions, or you look around, you just in a really visual, you just look around and see what you see, and just about what you make a meaningful question. So maybe I can start from the second part, yeah? Because recently I talked much with biologists, say, with chemists, and and they do have their kind of questions, and which leads to mathematical questions. For example, if you look at plants or trees, yeah? So can you say as a mathematician what they are? So a piece of a surface, yeah, is kind of, this we understand, yeah? Now look something like trees. So what you have here is also just exactly these two features. So on one hand, there is a very peculiar structure there. Yeah? They're not at all anything. Yeah? You have a tree, and there are leaves, and there are branches, and they can organize in a certain way. You immediately recognize it. Yeah? This is, by the way, another way how you recognize it. Again, it was a piece of meat, something almost without structure, which can tell you instantaneously a tree from an animal. Right? That's, by the way, well, the psychologists of vision work on that, yeah, and it's extremely unclear in principle how this could happen, yeah? Not just in detail, but in principle, it's impossible. Yes, if you think a little bit about that, how it could work, it just cannot work. We know that our response of the nervous system is very, very slow. Yeah, it's just well, tens of milliseconds, and the difference between a tree and an animal just you just try to describe it in short words, you see it's impossible. So, but however, we see something there. Like animals, they don't have this richness of shape, but they speak about trees or vegetation in general, right? You see here, there's definitely some regularity in these patterns. How to describe them? And indeed, there was discovered a generating mechanism for them, describing them up to some extent. The framework is a fractal framework, up to some extent, but not limited. But there was a mathematical mechanism discovered by what's his name? I forgot. They're called L systems, yeah, but so the name is Lindemeyer, yeah. I'm not certain about spelling. He was a biologist. He was kind of, for a while, he was a classical biologist and doing, I think, molecular biology, and then he switched to generating mathematical mechanisms for plants and immediately lost his job, yeah. And now he became very famous, and this is in computer science especially, the Lindemeyer systems are used. So that's a mathematical generating mechanism 4 planes, and is extremely close to what is called Markov partitions in dynamical systems. So it's a hyperbolic mechanism, but particularly it's kind of generating trees, a simple object. There is more to that. So there are some generating mechanisms which roughly give you the idea of that, but certainly they are by no means sufficient. So the mathematical question may ask what are simple mechanisms. In principle, they might be extremely simple, they're coded in very few words, which generates, however, the variety of vegetable forms. But there we have, on one hand, a large variety, on the other hand, it's very, very structurally organized. It's more interesting than what we have in the animal world. Actually, in the animal world, we also have it, but we don't see it, yeah? So if you look inside you, then you do have some trees, yeah? For example, the system of blood vessels, yeah? It also makes a tree. And it's an extremely beautiful tree, and just recently there was a lecture in the Statistical Mechanics Conference by somebody, Geoffrey West, who used this to explain some biological regularities. Looking at this huge tree, it goes in miles, yeah, in length, because there are microscopic things. It branches and branches. Actually, it doesn't branch too much, 5 or 6 times only. But still has a lot, 6 is a lot, yeah? Exponential function. And so there you may find geometrically attractive structures about which you may think. So another, of course, again, back in the biology, is the possible combinatorial arrangements of the brain connections, yeah, which allows you, say, to tell an animal from a plant. And again, it's a very primitive mechanism, and there are some non-trivial kind of mathematical models there. For example, if you want to explain the following phenomena, kind of from scratch, not really biologically, but as a mathematician, that we know so fast we don't know something. For example, if you ask the telephone number of the Bill Clinton, everybody knows he doesn't know it. How can you do it without searching your memory? Right? Don't have to say, I don't know of this, like computer will die, of this, not here. It was 45 minutes.
I think you were
I'm sorry, yeah. Okay, then just to say a couple of words about Bill Clinton, and that's it, yeah. So you don't know his telephone number, and there is a very beautiful mechanism due to Canerva. It's a computer scientist who gave a very beautiful kind of formal scheme of a memory, or iterative memory, and where the key point of that, how it works, is the concentration phenomenon. So I'll stop at this, yeah? It's concentration phenomenon.